For this video, we'll be discussing expectation values as well as eigenvalues and eigenfunctions. We'll start by discussing expectation values. Expectation values, or also they can be thought of as the expected average value of operators and wave functions. So let's set this up somewhat carefully. If we have a system described by a wave function psi, and so we have our system is in that state, and we're interested in some observable, right? Some quantity that we want to measure about the system, and that observable is represented by an operator. We'll call it A. Okay, so so far this is just kind of some generic state and some generic operator. We don't know the details about what measurement they represent and what kind of state the system is in, or what kind of system it is, period. Then the expectation value for the system and observable, in other words, the expected average value that you would observe by observing the system, that you would observe with the observable corresponding to the particular operator A, is given by this integral. The expectation value of A, so here we use square brackets to denote expectation value. Okay, and these square brackets, we're sort of borrowing notation from statistics. Often angle brackets in statistics or statistical physics, often angle brackets will represent some sort of average or expected average value. So that expectation value is given by the integral over all space of psi star A psi d tau, where d tau is our differential volume element, our sort of generalized volume element. And again, all space depends on the particulars of the system, the dimensionality, and there may be some restrictions on where a wave function has a non-zero value, and that may also be built into the all space, as we'll see shortly. So the expectation value, first of all, that's our expected average. In other words, we have a system that's governed by probability. And we would expect that if we conduct a series of measurements, each individual measurement is going to give a slightly different result, or perhaps very different result. And the net result is going to be, if you take all of those measurements together and calculate an average, you will get this expected average or expectation value. So there's a subtle difference between average and expectation value. Expectation value defines, say, is defined in terms of the probability that the system would have a certain value. And so the expectation value or the expected average is that, whereas an average value corresponds to not some hypothetical set of measurements, but an actual set of measurements. And we may circle back to that later. If not, it is covered in the PDF handout. Okay, so individual measurements are going to vary. They may vary, they may not. There is the case of them not varying. But typically, particles are going to be fuzzy and going to have some sort of range of possible position and momentum values that have some associated uncertainty. And so there's going to be a range of, if you either set up some number of identical systems and perform measurements on them, or perhaps you take the same system and measure it again and again, you're going to get different values each time. And that's going to reflect some uncertainty. But that doesn't mean we can't know anything about, say, the position or the momentum. We can still calculate the expected average. We can calculate the sort of standard deviation, which we'll talk about later. But so it's not that once we have a system that behaves probabilistically, all bets are off and we can't say anything about it. That's not true, right? We have laws of probability that tell us, that give us some idea what to expect. We just don't necessarily know what any one measurement is going to give us. And let's take a look at this integral for a moment. This looks very similar to expectation value in statistics for a probability density or a probability distribution function. So if we have from stats, if we have some probability density function, say P of x, that's our probability density function, and we have some value function, f of x, then the expected average value of f is going to be equal to the integral over, say, all space or all possible values of x of f of x times p of x times dx. So this is in the language of statistics applied to calculus applied to statistics. This is a moment, right? This is the say it's kind of like the centroid or the center of mass of f, in this case, this function. And another thing that we can observe from statistics is in the limit of infinite measurements, right? There's a correspondence between the actual measured value of f, measured average value of f, and the expected average. They should coincide. In other words, if we're rolling dice, we're going to get different die rolls each time you roll it, but if you roll it enough times, it will slowly eventually converge towards some sort of average number. So here's a couple of partial examples. If we want to, say, measure the position of a particle, going back to quantum mechanics, if we want to know where a particle is along the x-axis, on average, if we want to know its average position, that's going to be the expectation value of x. And it's for a system in some state psi, then the expectation value is going to be the integral over all space of psi star x psi dx. And then the next step is, of course, we would just replace this operator with its mathematical representation, which is just multiplication by x. And you'll see that this is, somewhat similar to this statistical example if we pause to consider that psi star psi is something like a probability density function. So that's simple enough. However, if we want to look at something like momentum, there's going to be a little bit more calculus involved in that the expectation value is going to be the integral over all space of psi star. And again, I'm being a little loose with using psi. Psi just represents the system in the state of interest that we're trying to study. And we would multiply by minus I h bar ddx. So we would not subtract I h bar ddx. Here, the minus is a sign, not the subtraction operation. So we have to be careful about that. When we have operators that have, they may have some additive terms. They may also just have some sign. And so we have to be a little bit careful about that. We could also use, instead of saying minus I h bar, we could use the equivalent expression h bar over I. And I'll leave that as an exercise to prove that those are equivalent, or to show that those are equivalent. Then we have our other wave function psi times dx. So what happens here is that we act the derivative on psi, and so if we say that psi prime is d psi dx, then this would be the integral of psi star, which is the complex conjugate of psi, times psi prime dx, and I neglected to insert here moving the constants out front. We'd have minus I h bar minus I h bar, the integral over all space. So moving the minus I h bar out front, we'd have the integral over all space of psi star times psi prime, i.e. the first derivative of psi times the differential volume element dx, integrating that over all space, and we would get a value for momentum. So reiterating, we would first take the derivative of psi, then multiply by those constants, minus I h bar, then multiply by psi star, then take the integral. And I'll go ahead and write those down because this order of operations, this order of attack is important. So first we take the derivative of psi. We can multiply that by the constants. Or we can hold off and tack the constants on at the last step. The important part is then you multiply by the complex conjugate of psi, i.e. multiply by psi star. Then we take the integral and we should end up with a function that no longer, because we've integrated over x, it should no longer contain x. It should be some value. And of course, we would multiply it by minus I h bar if we hadn't already. Okay, let's try a little bit more concrete example. For the x case, let's assume that we have an exponentially decaying wave function e to the minus x over 2a times 1 over square root of a, and that this wave function, so it needs that 1 over square root of a factor, which we could put in front. Let's go ahead and put that in front. And this would only have a value in the range between x ranges from 0 to infinity. Okay, so we have a wave function that starts at 0. It has no value below 0, and it goes to infinity. So that defines our space as ranging from 0 to infinity. Then if we plug that in to our integral, our expectation value for x is going to be the integral is going to be 1 over a. See, so this wave function is actually real everywhere, so the complex conjugate is equal, so psi star equals psi. We're going to get this 1 over square root of a factor out front. We'll have two of them because we have psi star psi. And our integral ranges from 0 to infinity of e to the minus x over 2a times x times e to the minus x over 2a dx. And of course we can combine some terms. Now at this point it's an algebra problem inside the integral, right? We've taken, there aren't any derivatives inside that are associated with this operator, so at this point inside the integral it's just an algebra problem. We can do a little bit of rearrangement, and this is going to be 1 over a integral from 0 to infinity. Again, we've defined our wave function as only having a non-zero value in this range from 0 to infinity, so we have to respect that. We have to set our integral limits to be consistent with that. We can't in one step say, oh, all space is from 0 to infinity, and then in the next space say it's something else. Okay, so then combining the exponential terms together, we get e to the minus x over a, because when you multiply exponentials together and exponential functions together, you add the arguments of the exponential. So we get e to the minus x over a, and then we can just put our x there, dx, integrate that. This is one of those integrals that you'll find in an integral table. And when you multiply all of this out, you end up with that the expected average value for position is a, where a is some constant that we can think of it as a decay length. And so this is saying that the average position is roughly one decay length for an exponential decay. And by the way, sometimes wave functions may have this kind of exponential decay form. This would be an example of tunneling. Tunneling tends to have these exponentially decaying wave functions. We'll perhaps talk about tunneling later. Okay, so sometimes we have to do integration. We may have to look up examples in integral tables or perform some integration by parts. In principle, I won't expect you to do integration by parts typically on a homework, never on an exam, but some standard integrals will show up, like integrals of sine and cosine and ordinary integrals of exponentials that are not multiplied by x. Okay, so that's an example using integration. Now it turns out that there's a special case. In some cases, we end up with a wave function. In some cases, we end up being able to skip integration, and because that really saves us some time and allows us to sort of move quickly through certain steps, that special case where we can avoid integration is particularly important, and so we need to take some time to talk about that case, and it has some definitions and some nomenclature associated with that. So let's take a look at how we can skip integration in some cases by looking at eigenfunctions and eigenvalues. So sometimes we have to integrate, sometimes we don't. And now we're looking at the case where we don't have to integrate, but this requires a little bit of setup. So it turns out that for many operators, but perhaps not all, there exists an eigenfunction such that acting our operator on this eigenfunction f is equal to some constant times f. In other words, acting the operator on the function returns a constant times the function. And this constant has an important value. It's called the eigenvalue. Oops. And the function is called an eigenfunction. And it's not eigen, although it's spelled very similar to, say, the name of Chrissy Teigen, right? The well-known model and personality, internet personality. That said, Chrissy Teigen says the actual correct pronunciation for her last name is Teigen, and it's based on German, and I believe it means self. So it's this self value or the self function. And let's see what to say next. Let's look at a quick example similar to what we saw before. Let's have an operator a simple differential operator. So typically eigenvalues are going to occur when there's at least a single derivative, maybe a second derivative in your operator somewhere. And then let's say our function, again, this is an example. This isn't the general case. This is a particular example where we have an operator given by d dx, and we have a function which is, say, e to the k x, where again this is an exponential function where e is the Euler's number that's used in natural logs and exponentials. Okay, so if we act our operator on our function f, we get d dx e to the kx. And the first derivative of an exponential like this is going to be k e to the kx. And so we get back the original function f times some constant. So we could say that the f is an eigenfunction of this operator. It may not be an eigenfunction of a different operator. So eigenfunctions are always defined in terms of an operator. So it's an eigenfunction of this operator, and we say that k is the eigenvalue, where we assume k is some constant. Another thing that we should state, there are some interesting properties of operators. And that is that all operators that correspond to observables, so physical observables, things that we can measure, have real eigenvalues. And another thing that we can say that I sort of hesitate to include because we're not going to do a lot with it, but this has to do with the fact that operators corresponding to physical observables so physical in the sense not meaning of physics, but rather physical in terms of having to do with physical reality, the real world. Physical observables, things that we can, at least in principle, measure, these have real eigenvalues. And anyways, so an operator that has real eigenvalues is called Hermitian. We're not going to deal a lot with that, but it may come up in that it's useful for proving operator orthogonality. So if we have, yeah, let's move on to that. So we call it Hermitian. That's kind of a waypoint. Then the next important concept is that it can be proven that if we have a Hermitian operator, so in other words, one that has a real eigenvalue, and there are two wave functions we'll call them psi1, psi2, and the wave functions have different eigenvalues. For the Hermitian, or so we'd say different real eigenvalues. I really shouldn't have the parentheses there. Then psi1 and psi2 are orthogonal. And so as it turns out, the eigenvalue, I'm not going to prove this necessarily right now, but as it turns out, if there are different eigenvalues, these correspond to different physical properties of the system. And if a system has different physical properties, say a different energy for psi1 versus psi2, so psi1 has a certain energy E1, psi2 has an energy E2, and E1 and E2 have different values, then these can't be the same state. You can't have two states that have different energies and have them be the same state. So it sort of makes sense based on what we know so far, but we haven't really proven it in detail. However, let me just sort of restate what I've said in words mathematically. If we have an operator A such that A psi1 equals A1 psi1, and operator A acting on psi2 gives A2 psi2, and A1 and A2 are real, and A1 is not equal to A2, then psi1 and psi2 are orthogonal. In other words, the integral of psi1 star psi2 over all space is 0. And we can say psi1 and psi2 are different states. Now, I have to be a little bit careful in that sometimes different states will have some properties that will be the same. Like, for instance, an electron can have the same energy as another electron, say the two electrons in a 1s orbital. One is spin up and one is spin down. The spin up electron and spin down electron are in different states, but they have the same energy level. They, however, have different spin. So we have to be a little bit careful. This is a little bit like the case of that all squares are rectangles, but not all rectangles are squares. So we have to be a little bit careful about misapplying this concept. So now we have a quick and easy way we can tell, in some cases, whether two states are different. If they have different eigenvalues for an operator that corresponds to an observable, then they are different states. And there's some more important properties of eigenvalues that we'll talk about later. We'll talk about, sorry, in just a moment. Another case, so we have to be careful. There can be what are called degenerate states that have the same energy, but they're different states. Like say spin up versus spin down electrons. Also, you can think of like say the three different p orbitals of the hydrogen atom. Say like three different 2p orbitals of a hydrogen atom. They correspond to different states. The shape is similar, but it's rotated 90 degrees. You have say a 2px wave function, a 2py, a 2pz wave function. These are different states. They occupy different regions of space. However, they're similar, right? They're related by rotation. But nevertheless, they're different states, but they have the same energy. So we say that they're degenerate. We'll talk more about that later as we get into degenerate states and the hydrogen atom and similar systems. Let me close by stating something really important about eigenfunctions and eigenvalues and expectation values. And that is, if we have an expectation value for A for some state psi, right? So I'll just put in a subscript here. That's for a system in state psi. We don't always put that there, but I'm just being a little pedantic here. Then that's going to be the integral of all space of psi star. Oops. Okay, and then if A psi is equals to a constant times psi, in other words, if psi is an eigenvalue of A, or eigenfunction of A, I skipped the en, eigenfunction, oh well. A little shorthand that I use. Some of these words get kind of long. Then if we plug that in to our integral, we're going to get our integral over all space of psi star. We act the operator on the corresponding wave function. That's going to give us the little eigenvalue A here. And then since that's a constant, we know from calculus we can just move that outside the integral. And if we assume without loss of generality that our wave function is normalized, and I'm not going to prove that we can assume that without loss of generality, but let's just impose that we assume normalized. Then we know what this integral goes to, and that's supposed to be a d tau there. This integral goes to 1, and so we get a. So therefore, the expectation value, oops, of an eigenfunction is the eigenvalue. Which we essentially just proved there. So I'll put a little QED. And this ends up being very useful. So this means that because we know the answers of some integrals, we know that our wave function is either normalized or is normalizable, then since that's true, then if we can rearrange things such that we end up with a normalization integral, we can replace an integral with 1, and we get just our eigenvalue back. And so the expectation value of an eigenfunction is the eigenvalue. So this ends up being very useful. Sometimes we can skip integration. And that will bring us to the next concept related to expectation values, which is it's related to expectation values. It's also a good general tool, which is a superposition principle. And that will be the subject of the next lecture video.